It may seem like we've done a lot of extra busy work unnecessarily. We get to put all of this to use to simplify our mass matrix by quite a bit. So, as we saw in the low order solution from Module 2, here's our mass matrix. Now in this case, our basis functions are going to be our Lagrange bases. And here's our mapping that's a result from us transforming from our elemental domain to our computational domain. And as we saw, for the choice of the Legendre roots for our interpolation points, this inner product is going to be 0 because these bases are orthogonal with respect to each other unless they're the same bases. So this becomes quite simply the Kronecker product times our associated quadrature weight. Now notice the Kronecker product means that it's only non-zero when both I and j are the same. So when we look at the sum of our solution approximation coefficients here, the only term that's non-zero is when the subscript on dq dt here is j. So therefore, for any one particular mass entry for a particular jth basis for our weighting function, we get this. Okay, so we've essentially been able to then reduce what was a full mass matrix in the linear solver from Module 2 case into something that's purely diagonal with all other terms 0. So this has several benefits. The matrix is trivially invertible, as well as it's very easy to determine what the component-wise effect on any one basis function for our weight. So if we put this in a vector form, we have this, where each of the diagonal terms in our mass matrix is just the associated quadrature weight.